Scientists just tested water from another star system, and it looks nothing like ours. The result is so extreme, it may change how we think planets are born. When 3I Atlas entered the solar system in 2025, astronomers expected something strange. Interstellar objects are always strange, because by the time one reaches us, it has already survived a journey through deep space that most things never make. But what scientists found in this one was not just strange. It was the kind of result that makes people stop, stare at the data, and ask the same question 3 times to make sure nobody messed up a decimal point. This comet is carrying water with a chemical fingerprint we have never seen before. Not in Earth's oceans, not in the comets of our own solar system, not even close. The water inside 3I Atlas is loaded with deuterium, a heavier form of hydrogen, at levels at least 30 to 40 times higher than in Earth's oceans, and way above what we see in normal comets around the Sun. And that one number may be telling us that the star system where this comet was born formed in conditions very different from ours. In this video, we're going to walk through the whole story in plain English, what 3I Atlas actually is, why scientists care so much about comets, what heavy water means, why this result shocked astronomers, how they even measured it in the first place, what it says about the birthplace of this comet, and why this one frozen object from another star system may be forcing us to rethink how common our kind of solar system really is. Because once you understand what this comet is carrying, it stops being just a cool sky story and starts looking like a message from somewhere else in the galaxy. First, let's talk about the visitor itself. In July 2025, astronomers spotted a new object moving through the solar system. At first glance, that may not sound unusual. New comets and asteroids get discovered all the time. Modern sky surveys scan huge parts of the sky every night, and they constantly pick up faint moving dots. Most of those dots turn out to be ordinary solar system objects, asteroids, comets, little leftover chunks from the early days of our own planetary neighborhood. But this one had a problem, or rather, it had the kind of problem astronomers love. Its path didn't make sense for something born here. When scientists calculated its orbit, they found that the object wasn't circling the Sun on a normal closed path like a planet or a typical comet. It was on a hyperbolic orbit, which is the cosmic version of a one-way trip. It came in from interstellar space, swung around the Sun, and will head right back out again. The Sun cannot keep it. This object is not part of our family, it's just passing through. That is why it got the name 3I Atlas. The 3I matters a lot. It means third interstellar object ever confirmed in the solar system. Not third comet, third interstellar object, period. In all of human history, after centuries of staring at the sky, building better telescopes, and trying to understand where we live, this was only the third time we had clearly caught something from another star system passing through our own. That alone would have made it important. But 3I Atlas had another feature that made scientists lean forward immediately. It was active like a comet. That is huge, because a dead rock from another star system is interesting, sure, but a comet is better. A comet heats up near the sun ice inside it, turns to gas. That gas flows out into space and forms a fuzzy cloud called a coma, sometimes with a tail. And once a comet starts doing that, astronomers can study the gases coming off it. In other words, a comet starts spilling its secrets. Comets are messy, they are dramatic. They hate privacy. That is why scientists got excited fast. 3I Atlas wasn't just a visitor from another star system. It was a visitor leaking chemistry. To understand why that matters, it helps to look at the two interstellar objects that came before it. Back in 2017, astronomers discovered 1I Oumuamua. That was the first confirmed interstellar object ever seen. It was weird from day one. It had an odd shape, unusual brightness changes, and later it showed a small unexplained push as it moved away from the sun. Some people got way too excited and started talking about alien spacecraft. That made headlines, but it was not the main story. The real story was simpler. Oumuamua was the first proof that material from another star system could pass through ours. The frustrating part was that Oumuamua didn't show a nice, obvious comet coma. It stayed chemically quiet, so while scientists could study its motion and brightness, they couldn't really read its full chemical makeup the way they wanted to. It was like having a locked suitcase from another country, but never getting to open it. Then in 2019 came 2I, Borisov. Now, Borisov was a gift. It looked like a comet. It acted like a comet. It outgassed like a comet. Scientists could study its chemistry, compare it to our own comets, and for the first time start doing real interstellar comet science instead of just orbital math. Borisov turned out to be unusual, but still somewhat familiar. It had lots of carbon monoxide, and that hinted at a colder origin than many solar system comets. Still, it felt like distant cousin weird, not total stranger weird. And then 3I Atlas arrived and basically said, "You thought Borisov was unusual? That's cute. From early observations?" Astronomers could already tell this comet was not ordinary. As it approached the sun, it became strongly active. It threw off gas and dust. Researchers started looking at the molecules in that gas, and some of the first chemical clues were already odd. The proportions of carbon dioxide and methanol didn't line up well with the normal patterns seen in most solar system comets. That suggested the ice in this comet formed in different conditions from the ones that shaped the icy bodies around our sun. Then something else happened. As 3I Atlas went through perihelion, the point where it was closest to the sun, its chemistry changed. The material coming off after perihelion didn't look exactly the same as the material coming off before. That matters because it hints that the comet may have layers. The outer layer may have been different from the material underneath, and that means this object may not just be strange overall. It may carry a layered record of its own history. Picture a frozen cake that sat in a freezer for millions of years, then got blasted with sunlight as it rushed past a star. The outer frosting starts melting first, then cracks open. Then deeper layers get exposed. If those layers formed under different conditions, the chemistry changes as the comet heats up. That seems to be part of what happened here. So even before the water result, 3I Atlas was already waving giant red flags. But the water result was the real turning point, because water is not just another molecule on the list. Water is the big one. When astronomers talk about comets, water is like the headline ingredient. Most comet ice is water ice. The other molecules are important too, sometimes very important. But water is the core story. If you want to understand where a comet formed, how cold its birthplace was, and how much of its original chemistry survived, water is one of the best places to look, except there is a catch. Water sounds simple. It isn't. At school, we learn that water is H2O, 2 hydrogen atoms and 1 oxygen atom. That part is true. But in chemistry, hydrogen has versions. The normal hydrogen most people imagine is just a proton with an electron around it. But there is another version called deuterium. Deuterium is still hydrogen, but heavier. It has a proton and a neutron in the nucleus. Same basic element, bigger core. That extra neutron changes things. If a water molecule contains one deuterium instead of one normal hydrogen, you get HDO. Scientists sometimes call that semi-heavy water. If both hydrogens are replaced, you get D2O, which is what people usually mean by heavy water. It looks like ordinary water. You can't spot it in a glass, but it behaves a little differently. It is denser. It freezes a bit differently. It boils a bit differently. And in biology, too much of it causes trouble. Now here comes the key idea. The ratio between deuterium and normal hydrogen in water is a clue about where that water formed. That ratio is written as D/H, or DH. And this is one of the coolest tricks in astronomy. By measuring the DH ratio in water, scientists can infer the kind of environment where that water formed long ago. It acts like a chemical memory. The universe leaves little marks in molecules, and if you're careful enough, you can read them later. Why does this ratio change from place to place? Mostly because of temperature. In very cold environments, certain reactions in space become more likely to put deuterium into molecules instead of ordinary hydrogen. Cold chemistry favors it, not because space is playing favorites, but because the energy balance of reactions changes at low temperatures. In plain language, when things get extremely cold, deuterium has an easier time sticking in certain molecular arrangements. That means water formed in extremely cold conditions can become enriched in deuterium. The colder and less disturbed the environment, the stronger that effect can be. So if you measure a high DH ratio in comet water, that is a sign. It means the water likely formed in a colder environment, or at least preserved chemistry from such an environment, better than water with a lower DH ratio. Earth's oceans have a known DH ratio. Scientists use that as a reference point. It is about 155.7 parts per million. You don't need to memorize the number. What matters is this. Earth's water has a certain fingerprint. Comets in our solar system often have more deuterium than Earth's oceans. That has been known for years. But usually they fall into a fairly limited range. Some are close to Earth's value. Some are maybe 2 or 3 times higher. There are exceptions, but not giant, crazy exceptions. The family resemblance is still there. That is why 3I Atlas was such a shock, because this thing didn't just come in a little high. It came in absurdly high. Before we get to that number, though, we need to understand how the measurement was made, because this is where the story gets even better. Scientists did not just point a telescope at the comet, see heavy water floating there, and call it a day. The measurement was difficult, indirect, and clever. The main instrument involved was ALMA. The Atacama Large millimeter-SOP-millimeter array in Chile, ALMA, is one of those machines that sounds boring until you realize what it can do. It is a group of 66 radio dishes high in the Atacama Desert, one of the driest places on Earth. The reason it sits there is simple. Earth's atmosphere contains water vapor, and water vapor messes with measurements of water in space. If you want to study faint signals from molecules far away, you don't build your telescope somewhere damp. You put it in a place so dry your lips start complaining, just from reading about it. ALMA works by detecting radio waves from molecules in space. Molecules rotate and vibrate in specific ways, and those motions produce radiation at very specific frequencies. Each molecule has its own pattern, like a barcode. If you detect that pattern, you know the molecule is there. Now, here's the annoying part. Regular water is notoriously hard to observe from the ground because our own atmosphere is full of it. Trying to detect water around a comet from Earth is a bit like trying to hear someone whisper water while standing under a waterfall. Some lines are blocked, some are weakened, and the whole thing becomes difficult. But the team studying 3I Atlas did detect HDO, the semi-heavy form of water. That mattered a lot, because if you detect HDO and at the same time fail to detect normal water above a certain level, you can still say something very powerful. You can place a lower limit on the DH ratio. In other words, you may not know the exact ratio yet, but you can know it has to be at least this high. That is what the researchers did. They observed the comet with ALMA. They found the spectral signal of HDO. They also studied methanol and used detailed computer models of the gas around the comet to estimate how much normal water could be present without producing a clear, detectable signal. That non-detection became a constraint. And when they combined the detected HDO with the maximum possible amount of regular water consistent with the data, they got a minimum DH ratio. And the result was brutal. The water in 3I Atlas appears to have a DH ratio at least 30 to 40 times higher than Earth's oceans. Ride that again, not 30 to 40% higher. 30 to 40 times higher. And compared with typical comets from our own solar system, the value is still more than 20 to 30 times higher. That is not a weird little wiggle in a graph. That is a giant red siren. If solar system comet values usually sit in one neighborhood, 3I Atlas moved to another country. Naturally, when a result is this extreme, the first reaction is caution. Scientists do not like giant claims unless they survive abuse. So the team checked the models, they tested assumptions. They used the missing regular water signal as a hard limit rather than just guessing. They looked at the methanol data. They built a physical model for how gas behaves in the comet's coma. They pushed on the result from different angles, and the lower limit stayed high. That is why this became a big story, and why the study landed in Nature Astronomy. It was not just a flashy headline. It was a serious result backed by a careful method. Now let's slow down and talk about why this number is such a problem for our old assumptions. To do that, we need to rewind all the way back to how stars and planets form. Stars begin in molecular clouds. These are giant cold clouds of gas and dust floating in the galaxy. They are huge, dark, and cold enough that chemistry behaves very differently inside them than it does in warmer regions. Temperatures can fall to around 10 Kelvin. That's around minus 263 degrees Celsius. In other words, space can get cold enough to make your freezer look like a tropical resort. Inside those clouds, atoms and molecules settle onto tiny dust grains. Those grains act like little chemical workbenches. Reactions happen on their surfaces. Water can form there. So can methanol and many other molecules. And because the environment is so cold, deuterium can get built into molecules more easily than it would in warmer places. So the water that forms in these very cold conditions can end up with a high DH ratio. Then gravity takes over. A denser part of the cloud collapses. A baby star forms in the center. A spinning disk of gas and dust forms around it. That disk is the place where planets, asteroids, and comets are born. But here's the important part. Not all of the original chemistry survives unchanged. As the young star turns on, the inner disk gets hot. Material heats up, evaporates, reacts, mixes, and sometimes gets chemically reset. The original deuterium-rich signature from the cloud can be weakened or partly erased. The outer disk stays colder, so icy bodies forming far away can preserve more of the old chemistry. That is why comets are so interesting. They are often built in cold outer regions and can preserve ancient chemical fingerprints from the earliest stages of a planetary system. They are little freezers full of history. Our own solar system comets seem to preserve some of that ancient cold chemistry, but not in an extreme untouched way. Their DH ratios are higher than Earth's, but usually still within a fairly narrow band. That suggests the material in our solar system was processed, mixed, heated, and reworked to some degree before and during comet formation. 3I Atlas, by contrast, seems to have held on to a much stronger cold origin signature. So what could explain that? There are a few main ideas. The first is that the comet formed in a star system born in a colder, quieter region than our own solar system. Maybe the parent molecular cloud was especially cold and dense. Maybe the whole system evolved in a way that preserved that original chemistry better. Less heating, less mixing, less chaos. The second idea is that the home system may have started with similar raw material to many others, but then processed it very differently. In our solar system, there was likely a lot of movement and mixing. Giant planets shifted things around. Material travelled inward and outward, hotter inner disk material and colder outer disk material interacted. Those processes blur chemical differences. They stir the pot. Maybe in the 3I Atlas system, the pot was barely stirred. If that happened, the outer icy bodies could remain much more pristine, still carrying water chemistry close to what existed in the original cold cloud. There is also a third possibility worth thinking about. 3I Atlas may have formed very far from its parent star, farther than many of our own comets formed from the Sun. The farther out you go, the colder things stay, and the less processing happens. If this comet was born in the deep outer edge of its system and later got kicked out, that could help explain why its chemistry looks so extreme. And yes, got kicked out is probably exactly what happened. Interstellar objects do not usually leave their home systems politely. Most likely, 3I Atlas was ejected. A giant planet may have flung it out during a close gravitational encounter, or a nearby passing star may have disturbed its orbit, or a changing system architecture may have destabilized a whole population of icy bodies and sent some of them into interstellar exile. Our own solar system likely did the same thing many times. Jupiter, especially, is the great cosmic bouncer. It has probably kicked out huge numbers of small bodies over the history of the solar system. If alien astronomers elsewhere ever detect one of our own ex-comets passing through their sky, that would be the same kind of story in reverse. So 3I Atlas is not just a comet from another star. It is a refugee of planetary system violence. It formed somewhere, got thrown out, wandered the galaxy, and eventually crossed our path. And now it is telling us where it may have come from, chemically speaking. At this point, somebody usually asks a fair question. Could interstellar travel itself change the DH ratio? After all, this comet spent who knows how long in deep space. Could cosmic rays, solar heating, or surface processing fake an extreme result? That is a smart challenge, and scientists have thought about it. The short answer is, not likely enough to explain a difference this large. Surface chemistry can change some things. Cosmic rays can alter the outermost layers of ice. Sunlight can remove more volatile material from the surface when a comet passes close to a star. Heating near the sun can change what comes off first. But isotopic ratios like this, especially in water, are generally much more tied to formation history than to short-term surface changes. You can weather the paint on a car, but that doesn't turn a bicycle into a submarine. The scale of the 3I Atlas difference is too large to be easily explained away by travel damage. That is one reason the result is so important. It looks primordial. It looks like inherited chemistry, not just cosmetic damage. Now, remember earlier when I said 3I Atlas already looked odd before the water result? Let's connect that with what we know now. The comet showed unusual ratios of carbon dioxide and methanol. It changed chemically around perihelion. It displayed strong activity. Now, add an extremely high DH ratio in water. All of those clues point in the same direction. This comet was not built under normal solar system-like conditions. When independent oddities all start pointing the same way, the story gets stronger. It's like if someone tells you they found a house with purple smoke coming out of the chimney. Weird, but maybe explainable. Then they tell you the windows are upside down. Then they tell you the front door is on the roof. At some point you stop saying, maybe that's nothing, and start saying, okay, this is clearly not a normal house. That is where 3I Atlas is. Let's talk more about the water itself, because this is where the story gets personal in a strange way. Every glass of water you drink carries a history. The water in your body was part of Earth's long chemical story. It probably spent time in oceans, clouds, rivers, ice sheets, underground rock, and living cells long before it reached you. But go back far enough, and that water also came from the early solar system. Some of it may have been delivered by asteroids, some may have come from icy bodies. Some may trace back to water formed before the sun itself existed, inherited from the molecular cloud that made our solar system. In other words, water is a record keeper. That is why comparing Earth's water to comet water matters. For years, scientists have used DH ratios to ask where Earth's water came from. If comets had exactly the same DH ratio as Earth's oceans, maybe comets delivered most of our water. If their DH ratios are mostly higher, then maybe asteroids or mixed sources played a bigger role. That debate is still active, and the answer is probably a blend. But the broader point is clear. DH is not just a chemistry number. It is a clue to planetary history. Now imagine finding water from another star system with a DH value far outside the range we are used to. That means one of two things. Either our solar system is more chemically specific than we realized, or planetary systems across the galaxy are far more diverse than we assumed. Possibly both. And that brings us to one of the biggest questions in astronomy. How typical is our solar system? Humans have a bad habit of assuming local experience is normal. For a long time, we thought the planets of our solar system probably looked like the typical planets around other stars. Then we found hot Jupiters, super-Earths, mini-Neptunes, tightly packed systems, weird resonances, and worlds orbiting two stars at once. Suddenly, our solar system stopped looking so standard. Then we thought maybe chemistry might be more universal. Water is water, right? Well, yes and no. A water molecule is still a water molecule. But the isotopic makeup of that water can tell a very different story. And 3I Atlas is saying maybe even something as familiar as water carries far more local flavor than we thought. That matters not just for comet science, but for planets, atmospheres, and maybe even life. Now let's be careful here, because this is where it gets easy to drift into nonsense. So let's stay grounded. Heavy water in large amounts is bad news for Earth life. If you replace too much ordinary water in living organisms with heavy water, chemistry slows down. Cells divide badly, enzymes misbehave. Biology starts stumbling over its own feet. That has been shown in lab experiments. But that does not mean a planet with higher deuterium water could never support life. It means Earth life, built in Earth's water, would not love that switch. Those are not the same statement. If life arose on a planet whose water naturally had a somewhat different DH ratio from the beginning, then any living chemistry there would have evolved under those conditions. It would not be Earth life shoved into a new bathtub. It would be life shaped by that environment from the start. We do not know how far that flexibility goes. Maybe small changes are fine and large ones are not. Maybe some chemistries work and others break down. Maybe heavy water-rich environments strongly limit biology. Or maybe life, as usual, finds a way and surprises us. The honest answer is, we do not know yet. But 3I, Atlas, tells us this question matters more than before. Because if planetary systems can produce water chemistry that differs this much, then the range of environments where planets begin may be much broader than the narrow Earth-centered picture we often carry around in our heads. Now, before we go too far down the life road, let's come back to the measurement itself. Because one of the most interesting parts of this story is how much scientists learned from something they didn't see. Usually, when people think of discovery, they imagine seeing something directly. Telescope sees object. Scientist points, big reveal, but astronomy often works like detective work. Sometimes the missing thing is the clue. In this case, the researchers detected HDO, but did not get a confident direct signal from normal water. And instead of shrugging and going home, they used that absence as a constraint. That tells you a lot about how modern astronomy works. The data isn't just a yes or no. It's a whole system of limits, models, probabilities, and physical rules. If there had been lots of ordinary water, ALMA should have seen it above a certain threshold. It didn't. That means there cannot be too much of it, at least not under the observed conditions. So even not seeing a molecule becomes informative. Then the team added the methanol data, the comet's temperature estimates, gas expansion behavior, and spectral line modeling. The result is not just we saw HDO. The result is, given what we saw and what we should have seen but didn't. And the physics of gas leaving the comet, the DH ratio, has to be at least this high. That kind of work is easy to underestimate when you just hear the final headline. But it is the backbone of the claim. And yes, this is why big science papers often come with lots of modelling, because space does not hand out neat labels. It gives hints, and scientists have to build the full picture. Now let's look at the idea of less processed water, because that phrase shows up a lot in discussions of 3I Atlas. When astronomers say material is less processed, they mean it has changed less since its earliest formation stages. It has been heated less, mixed less, irradiated less, chemically reworked less. It is closer to the original stuff from the molecular cloud. Think of snow on a mountain. Fresh snow at the top is fluffy and clean. As it moves downhill, it gets packed, melted, refrozen, mixed with dirt and trampled. By the time it reaches the bottom, it is still water, but the record of its original state is partly lost. Less processed material is like finding a pocket of old mountain snow still preserved in the shade. The water in 3I Atlas may be exactly that kind of pocket. a preserved chemical snapshot from a colder and less disturbed birthplace. And if that is true, this comet becomes more than an oddball. It becomes evidence that not all protoplanetary disks erase their original cloud chemistry to the same degree. Some systems may preserve ancient material much better than ours did. That would be a big deal for planet formation models, because a lot of our current thinking is based on the solar system as the best studied example. That makes sense. It is the only planetary system we can poke directly, but it also creates a trap. We can accidentally mistake familiar for universal. 3i, Atlas, is helping smash that trap. Let's also talk about the likely home environment of this comet in more detail. What kind of star system might produce an object like this? One possibility is a system around a smaller, cooler star than the Sun. Lower mass stars produce less heat, so disks around them can remain colder in more places. If the disk stayed cold farther inward, more water could preserve a high DH signature. And since red dwarfs are the most common stars in the galaxy, that possibility is especially interesting. It raises the question of whether many planetary systems around red dwarfs might have water chemistry very different from ours. Another possibility is a sun-like star born in a colder than usual part of a molecular cloud. Even stars of similar mass can start with different chemical setups depending on where they form. The galaxy is not one giant uniform soup. It is patchy. Some star-forming regions are crowded and noisy, with massive stars blasting radiation everywhere. Others are quieter and colder. Those differences matter. A third possibility is that the home system had a very different dynamical history. Maybe fewer giant planets, maybe giant planets in different places, maybe less migration, maybe a calmer disk. Less mixing means more chemical memory survives. And of course, these ideas are not mutually exclusive. The system could have been colder, quieter, and dynamically calmer all at once. That is part of what makes 3i Atlas so frustrating and so exciting. One comet gives clues, but not a full biography. We may never identify its exact home star. People often ask whether we can trace interstellar objects back to the star systems they came from. In theory, sometimes maybe. In practice, it's hard. These objects travel for enormous stretches of time. During that time, they pass through a galaxy full of moving stars, changing gravitational fields, and small perturbations that slowly alter their paths. Tracing them back exactly is like trying to figure out where one leaf came from in a windy forest after it has blown around for 1,000 miles. You can sometimes narrow down the broad region, maybe even a few candidate stars, but confidence drops quickly the farther back you go. So the chemistry may end up telling us more about 3i Atlas's birthplace than its orbit does. That is a weird and beautiful idea. We may not know which star it came from, but we may still know what kind of place it was. Now, let's zoom out again and look at why interstellar objects matter beyond this one comet. Before 2017, interstellar objects were almost theoretical from an observational point of view. We assumed they existed because planetary systems form messy and should eject debris. But we had not seen one with certainty. Then Oumuamua arrived, then Borisov, then 3i Atlas. In less than a decade, the category went from 0 confirmed examples to 3. That tells us something important. These things are probably not rare, they are just hard to spot. There may be huge numbers of interstellar objects passing through the solar system all the time, most of them too small or too faint for current surveys to catch. As sky surveys improve, We should find more, maybe many more, and every one of those objects is a free sample. Think about how crazy that is. The galaxy is vast beyond common sense. Other planetary systems are too far away to visit. Their comets are too faint to study in fine detail while they orbit distant stars. But sometimes a piece of one of those systems gets thrown out, wanders through space, and comes right to us. It is as if the galaxy occasionally mails us a package. We are only now learning how to open those packages. This is why future telescopes matter so much. The Vera C. Rubin Observatory, for example, is expected to transform this field. It will scan the sky with incredible speed and depth, and it should find many more moving objects, including likely interstellar ones. Once scientists know such an object is coming in early enough, they can line up telescopes across the world and in space to study it from multiple angles. Instead of treating each one like a once-in-history miracle, we may eventually get to compare dozens. And once you have dozens, the science changes completely. With one or two objects, everything feels anecdotal. With 10, patterns emerge. With 50, you can start talking about populations. Are most interstellar comets chemically familiar or chemically wild? Is 3I Atlas a rare freak or the first member of a common class we just hadn't seen before? Do objects from certain parts of the galaxy show particular signatures? Do some systems eject more ice-rich bodies than others? Those are the kinds of questions that become possible once the sample grows. Right now, we have one chemically quiet weird object in Oumuamua, one chemically interesting but somewhat familiar interstellar comet in Borisov, and one chemically outrageous interstellar comet in 3I Atlas. That is already enough to tell us the galaxy does not make one standard flavour of small body. Now let's return to the phrase that really set off alarm bells in the scientific community. Record deuterium enrichment. That phrase matters because astronomers had already studied DH in lots of contexts. They had measured it in Earth's oceans, in meteorites, in comets, in parts of interstellar space. They already knew that cold environments can produce enriched deuterium. So the discovery was not that deuterium can be high somewhere in the universe. The discovery was that a real comet-sized object from another system showed up carrying an enrichment far beyond the range known for similar bodies in our own solar system. That makes 3I Atlas a bridge between two areas of astronomy that often feel separate. On one side, you have astrochemists studying cold clouds, disks, and molecular lines in faraway star-forming regions. On the other side, you have planetary scientists studying comets and asteroids as solid bodies. 3I Atlas connects them. It is cold cloud chemistry wrapped into a cometary object and delivered right into planetary science territory. That is why this one result is bigger than weird comet has weird water. It ties together star formation, disk evolution, comet chemistry, planetary system diversity, and maybe habitability. And when one observation touches that many fields at once, people pay attention. Let's talk a little about the challenge of universality, because this is where the bigger philosophical shift happens. Scientists often ask whether some property is universal. Is water chemistry broadly similar across most planetary systems? Are the building blocks of planets roughly the same everywhere? Is the path from molecular cloud to comet to planet, basically, one standard recipe with minor variation? 3I Atlas doesn't destroy the idea of shared physics. Hydrogen is still hydrogen. Water is still water. Gravity still works. But it does challenge the idea that the chemistry of planetary systems falls into a narrow familiar band. If water isotopes vary this much, then the starting chemistry of planets can vary this much too. That could affect all sorts of things. How ices form, where snow lines sit, how much water reaches rocky planets, what kind of organics are delivered, and how early chemistry behaves on young worlds. Again, none of this means Earth is special in some dramatic movie trailer way, but it does mean Earth might not be the centre of the possible range. We may be one point in a much larger spread, and honestly, astronomy has been teaching us that same lesson for years. Earth is not the centre, the Sun is not the centre, the Milky Way is not the centre, our planetary architecture is not the centre, maybe our water chemistry is not the centre either. That is not depressing, that is thrilling, because every time we learn we are not the default, the universe gets bigger. Let's spend some time on another important question. How certain are we, really? This matters because people hear a wild result and sometimes assume it is either absolutely proven or total nonsense. Science is usually messier than that. Here is the careful version. The strongest claim right now is not, we know the exact DH ratio of 3I Los Atlas water. The strongest claim is, we have a strong lower limit. And even that lower limit is already astonishingly high. That is a meaningful distinction. If future data detects normal water more directly, scientists may refine the number. The exact value could shift. But unless something is deeply wrong with the interpretation, the big picture seems hard to escape. The water in this comet is far more deuterium-rich than water in Earth's oceans, and far more enriched than water in normal solar system comets. That is enough to matter even before the exact final value is nailed down. Also, one object does not define the whole galaxy. This is another important caution. We cannot say, based on 3I Atlas alone, that most planetary systems have strange water, or that our solar system is rare in a strong statistical sense. We do not have the numbers for that. What we can say is that at least some systems make objects with water chemistry wildly different from ours, and that fact alone already expands the map. Think of it like discovering one tree species in a forest. You thought you knew well. One tree doesn't tell you the whole forest. But if the tree is unlike anything in your field guide, your field guide needs an update. That is 3I Atlas. Now let's go back to the comet's behavior around the Sun, because I think that part deserves more attention. When 3I Atlas got closer to the Sun, astronomers saw strong activity. That means solar heat was driving gas out of the nucleus efficiently. After perihelion, the chemical output changed. That may sound like a small technical detail, but it could be telling us something important about the comet's structure. One idea is that the outermost layer of the nucleus had been altered during its long interstellar journey. In deep space, comets are bombarded by cosmic rays. Over long times, those can change the surface chemistry of ice and dust, breaking molecules, reforming others, darkening the surface, and maybe creating a kind of processed crust. Then, when the comet comes near the Sun, that crust starts cracking and peeling back. Fresh, deeper material, preserved better from the original formation environment, becomes exposed. If so, the changes seen around perihelion might be like cutting into a layered frozen dessert and finally seeing the inside. Another idea is that the comet formed with genuine layering from the start. Maybe different waves of material built it over time in slightly different temperature zones of its home disk. If those layers survived, solar heating could reveal them one by one. Either way, 3I Atlas may not just be chemically unusual, it may also be structurally informative. It could carry a layered archive of both formation and interstellar aging. That makes scientists very eager to study it more before it fades from view. Now let's talk about what else researchers may want to measure. Water is huge, yes, but it is not the only clue. Carbon isotopes could help. Nitrogen isotopes could help. Oxygen isotopes could help. The abundance of carbon monoxide, ammonia, hydrogen cyanide, formaldehyde, complex organic molecules, and sulfur-bearing species could all help. The more molecular fingerprints you collect, the better you can reconstruct the physical conditions where the comet formed. Think of it like solving a crime scene. One fingerprint helps. 10 fingerprints, a shoe print, a receipt, and a security camera image help a lot more. That is why astronomers are racing the clock. 3I Atlas is leaving. Every week matters. Every new observation can tighten the story. There is also a technical reason the comet is so valuable. Interstellar objects give us a kind of ground truth check on models of distant systems. Usually we study faraway disks and clouds through remote light only. We build models and compare them to spectra, but we cannot pick up a chunk of those systems. An interstellar comet is not a full sample return, but it is closer than anything else we have. It turns distant chemistry into a local target. That makes 3I Atlas important, not just because it is weird, but because it lets us test whether the chemical extremes we infer in distant star-forming regions actually survive into solid bodies. The answer now seems to be yes. Cold cloud chemistry can survive into real comet-like objects under the right conditions. That is a strong statement. Now let's bring Earth's water back into the story more directly. Because people always want to know, does this tell us anything about where our own water came from? Indirectly, yes. For years, scientists have debated how much of Earth's water came from comets versus asteroids versus direct inheritance during planet formation. One reason this debate matters is because water is essential for Earth's surface environment and life. Understanding its source helps us understand how habitable planets get wet in the first place. The fact that many solar system comets have DH ratios higher than Earth's made it harder to argue that comets alone supplied all ocean water. Asteroids seemed like a better match in many cases. But because different small bodies have different values, the real answer is likely a mixture. What 3I Atlas adds is perspective. It shows that the solar system's range, which once seemed broad enough, may actually be a very local range. Other systems can be much more extreme. So rather than directly solving Earth's water story, 3I Atlas reminds us that Earth's water story happened inside one particular chemical context. It is our story, not the universal one. That matters if you're thinking about exoplanets too. When astronomers study worlds around other stars, they often ask whether a planet lies in the habitable zone, where liquid water could exist on the surface. That is a useful first filter. But 3I Atlas is a reminder that not all water inventories are identical. Two planets can both have water, but the history and isotopic makeup of that water may be quite different. That may sound like splitting hairs, but it is not. Chemistry matters. Starting conditions matter. Delivery pathways matter. A planet's water story depends on the small bodies that formed in its system and the dynamical history that moved those bodies around. If your system makes comets with very strange water chemistry, your planets may inherit that difference. Now, Does that mean habitability changes? Maybe, maybe not. But it means the question is richer than, is there water, yes or no? That is the kind of complexity astronomy keeps uncovering. The closer we look, the less simple the universe becomes. Let's also say something about scale, because the numbers are so extreme that they can lose meaning if we do not anchor them. Imagine a town where almost every house has between 1 and 3 trees in the yard. Some have 1, some have 2, some have 3. You get used to that being the normal range. Then one day you visit another town and see a house with 40 trees in the yard, not 40. Suddenly you realize your old picture of what counts as a yard with trees was very local. That is basically what happened with 3i Atlas. Solar system, comet water usually lives in one kind of range. 3i Atlas is not sitting at the edge of that range. It jumped the fence. That is why even the lower limit is enough to make people rethink things. Now, I want to spend a bit more time on ALMA, because the telescope itself deserves some appreciation. ALMA is a masterpiece of modern astronomy. It sits high in the Atacama Desert because air there is thin and dry. The dishes can be spread apart and combined into a giant effective instrument using interferometry. That gives it tremendous sensitivity and resolution in millimeter and sub-millimeter wavelengths, which are perfect for studying cold gas and molecules. A lot of the most important chemistry in space is invisible in ordinary light. You need radio and infrared tools to see it. ALMA is one of the best we have for that job. It has transformed how we study protoplanetary disks, star-forming regions, galaxies, and now interstellar comets. Without instruments like ALMA, 3i Atlas would still be fascinating as an orbit, but the deep chemical story would remain hidden. This is something people often miss when they talk about science funding. You do not build an observatory like ALMA for one discovery. You build it because the universe keeps throwing impossible-looking opportunities at us. And when they arrive, you want the tools to be ready. 3i Atlas is a perfect example. Nobody planned this comet. Nobody scheduled it 10 years in advance. It showed up because ALMA existed. Scientists could act fast. That is how a lot of the best science happens. Preparation meets surprise. Now let's talk about the human side for a moment. Imagine being on that research team. You get word that a new interstellar comet has been found. Everyone is already buzzing because interstellar objects are rare and precious. You get observing time. The data arrives. You run the analysis, and then the HDO signal appears stronger than expected. You check the model. You realize the implied DH lower limit is insane. You assume something is wrong. You rerun everything. The result stays. Those are the moments scientists live for and fear at the same time, because a spectacular result is exciting, but it is also dangerous. If you rush, you can embarrass yourself. So the team has to slow down, check assumptions, compare methods, make sure calibration is solid, make sure no atmospheric effect or line confusion is fooling them. Then, once the number survives the stress test, the emotional tone changes. It becomes one of those rare moments when a dataset stops being just data and turns into a discovery. That is worth remembering. Behind every big result, there are people staring at screens, asking careful questions, trying not to fool themselves. And when the result survives that process, it earns its weight. Now let's step further back and think about what this means for planetary systems as a whole. A planetary system is not just planets. It is a full ecosystem of gas, dust, rocks, ice, migration, collisions, and leftovers. The leftovers matter. Comets and asteroids are not random junk. They are archival material. They preserve chemistry from the system's youth. They deliver volatiles to planets. They trace the architecture of the disk they came from. That is why one interstellar comet can tell us something about an entire lost system. 3I Atlas likely formed as one small icy body among many. Its chemistry suggests its whole neighbourhood may have been cold and chemically distinct. If that is true, then whatever planets existed in that system were inside a different volatile environment from ours. That does not mean the planets were bizarre, but it means their starting ingredients may have been different. And starting ingredients matter. A cake made with slightly different flour, sugar and butter can still be a cake. A cake made with salt instead of sugar is another story. Planetary systems work like that too. Same laws, different ingredients, different outcomes. Let's also not forget that 3I Atlas only reached us because its home system had a way to eject icy bodies into interstellar space. That tells us something about system architecture too. Strong ejection often points to giant planets or strong gravitational disturbances. In other words, the parent system may have had big players moving little bodies around. So even without seeing its planets, we can guess the system was not static. It was active enough to throw one of its comets into the galaxy. Now, can we say which kind of planets were there? No, not from this alone. But the fact of ejection hints that the system had enough gravitational muscle to clear house. Here is another big implication. The Milky Way may be full of chemical diversity that we are only now starting to sample directly. The galaxy has hundreds of billions of stars. Those stars formed over different times in different places, from clouds with different histories. Some regions were rich in heavy elements, some were poorer. Some were bathed in radiation from nearby massive stars. Some were isolated and quiet. Some clouds were colder, some more turbulent. Why would we expect all those environments to produce nearly identical small body chemistry? In hindsight, maybe we shouldn't have, but until interstellar objects arrived, most of our direct examples came from one solar system, ours. We knew diversity had to exist in principle, yet our real sample was narrow. 3I Atlas is a loud reminder that the galaxy has been running chemical experiments on a gigantic scale for billions of years. And sometimes one of the results of those experiments drifts into our backyard. Now I want to tackle something else people sometimes get wrong. They hear water from another star system is different from Earth's, and imagine the comet contains some exotic liquid unlike water. That is not the claim. This is still water. It is not alien goo from a sci-fi movie. The weirdness is in the isotope ratio. The recipe still says hydrogen and oxygen. What changes is the relative amount of heavy hydrogen. That may sound subtle, but subtle chemistry can matter a lot. If you swap ingredients at the isotope level, many physical properties stay similar, but some chemical behavior shifts enough to be scientifically huge. And in astronomy, isotopes are gold because they preserve memory. Two molecules can look basically alike in everyday life and still tell totally different origin stories. That is why isotope science is so powerful. It lets you separate what a thing is from where a thing came from. Now, I also want to talk about the role of absence in the bigger meaning of this result. Not just the absence of a water signal, but the absence of universality. One thing scientists often look for is some sign that chemistry smooths itself out over time. A kind of cosmic averaging process. You start with different clouds, but maybe most disks process things enough that by the time comets form, everyone ends up in roughly the same ballpark. 3i Atlas argues against too much smoothing. At least in some systems, the original differences remain strong, very strong. That means the galaxy may preserve local history better than we thought. Planetary systems may carry a lot of memory from the exact place and conditions of their birth, and that is kind of amazing. It means if you could sample enough small bodies from enough systems, you might eventually read a map of galactic history in them. Not just this came from some star, but this came from a system born in these kinds of conditions. That is an incredible thought. Little icy bodies as galactic memory sticks. Now, let's spend a moment on the paper's broader message. The Nature Astronomy result does not say all existing models are wrong. It says the space of possible outcomes is broader than many models assumed. That is how science usually moves. Not by replacing one simple truth with another, but by widening the field and forcing models to handle more reality. If a model of a planet formation naturally produces only comet water in the narrow range we see in the solar system, 3i Atlas becomes a problem for that model. The model now has to explain how some systems preserve much more deuterium-rich water, or it has to admit it was too solar system-centered. This kind of pressure is healthy. Science grows by getting punched by data, and 3i Atlas landed a good punch. Let's go a little deeper into why colder formation means more deuterium in water, but keep it simple. In cold space, chemistry slows down and certain reactions become easier relative to others. Deuterium, because it is heavier, changes the energy balance just enough that in low temperature environments it can get favored in some molecular pathways. Over time, that means molecules forming in those regions, including water, can end up with more deuterium than you would expect from the overall cosmic average. Then, if that material stays cold and relatively untouched, the deuterium-rich signature survives. If it later gets heated strongly, mixed with warmer material, or repeatedly recycled through reactions, that signature can be reduced. So high DH is not just cold once, it is often cold and preserved. That distinction matters. It tells us not only about formation, but about survival. 3i Atlas may therefore be telling us both that its parent environment was very cold and that the system did not later erase that record. That is a double clue. Now, if you're wondering whether ordinary people should care about this at all, I think yes, and not just because space is cool. The reason is that this discovery touches a very human question. How common is a world like ours? Not Earth-like in the movie sense, not little green aliens and ray guns. I mean chemically Earth-like, water-like in the way our world is water-like, planet formation like ours, delivery of life-friendly ingredients in familiar patterns. For a long time we had to ask that question almost blind. We could see stars. Then we found exoplanets. Then we started measuring some atmospheres. But we still lacked actual material from other systems. Interstellar objects are changing that. They are the first direct messengers. And the first few messengers are already telling us that, like ours, may be only one branch of a much bigger tree. That does not tell us whether life is common or rare. If anything, it cuts both ways. Maybe life needs a fairly narrow water chemistry window, in which case our kind of system could be more special than we hoped, or maybe life is chemically flexible, in which case the range of places where it can start may be wider than we imagined. Right now, the honest answer is that we don't know. But thanks to 3i Atlas, we know the question is not small. Now let's think about future missions, because this is the part where science fiction slowly starts turning into engineering. There are already mission ideas built around catching or intercepting unusual comets. The European Space Agency's Comet Interceptor mission, for example, was designed with surprise targets in mind. The basic idea is very smart. Instead of waiting for a target to appear and then starting to build a spacecraft, you launch the spacecraft first and park it in space. Then, when a good target shows up, you redirect it. That kind of strategy makes a lot of sense for interstellar objects, because they do not wait around. By the time one is discovered, the clock is already running. Could we send something to 3i Atlas itself? In practice, that is very hard. It is moving fast. Space missions take time. Matching speed with an interstellar object is brutal. But the dream is alive for future cases. And one day, if we intercept one up close, the science payoff will be enormous. Imagine a spacecraft flying through the coma of an interstellar comet, tasting its gas directly, imaging the nucleus, measuring isotopes in detail, maybe even collecting dust. That would be one of the great scientific moments of the century. A sample return would be even more ridiculous in the best way possible. Material from another star system brought into a lab on Earth. Isotope measurements, organics, mineralogy, microstructure, everything. That would be a generational discovery. We are not there yet, but 3i Atlas is exactly the kind of object that makes people want to get there faster. Now, I want to return to the issue of layered chemistry in this comet, because it opens another possible interpretation that is easy to miss. Suppose the outer parts of 3i Atlas were changed during its interstellar travel or during early heating in our solar system passage. Suppose deeper layers are even more pristine. Then what we have measured so far might not even represent the most original material inside the comet. In that case, the chemistry could become even more interesting as more layers are exposed. That is one reason follow-up observations matter so much. A comet is not a static rock. It evolves as sunlight works on it. The object you observe before perihelion is not exactly the same observed state as after. Watching that evolution can reveal internal structure and compositional layering. So 3i Atlas may still have more to say, and that is part of why this story feels unfinished in a good way. We are watching science happen in real time. Now let's compare the three interstellar objects we know about, because the contrast is useful. Oumuamua told us interstellar objects exist and can be dynamically weird. Borisov told us an interstellar comet can be chemically measurable and at least partly comparable to our own comets. 3i Atlas is telling us interstellar comet chemistry can go far beyond the range we know from home. That progression is kind of amazing. In less than a decade, the field has gone from do these things exist to how diverse are their isotopes. That is fast. It also means the next object could surprise us again in a completely different way. Maybe an interstellar asteroid rich in metals, maybe a comet with bizarre organics, maybe an object that looks ordinary dynamically but chemically wild. The field is young enough that almost any new data point can reshape the map. This is one of the rare times in science where we are truly at the beginning of a new category, not refining the 10th decimal place of something old, but opening a new drawer and finding we have no idea what is inside. Now let's talk briefly about why this discovery is not just about chemistry nerds, even though yes, chemistry nerds are having the time of their lives. At a deeper level, this is a story about cosmic context. We live on a planet where water feels ordinary. We wash with it, drink it, cook with it, complain when it rains too much. Complain when it doesn't rain enough. Water feels like the most normal thing in the world. But space keeps reminding us that normal is local. Water on Earth has one history. Water in our solar system has a family of histories. Now, water from another system is showing up with a fingerprint so different that it forces us to think bigger. The thing we call ordinary water may just be our local dialect of a more varied galactic language. That idea is hard not to love, because it means the universe keeps depth hidden inside familiar things. Now, let's address one more challenge. Could the measurement somehow reflect not unusual water, but unusual comma physics? In principle, any time you infer abundances from a gas cloud, the physical model matters. Gas temperature, expansion speed, density distribution, sunlight effects, and line excitation all play a role. If the coma behaves in a strange way, a naive analysis could mislead you. That is why the modelling in this study matters so much. The authors did not just convert signal strength to abundance with a simple one-step equation. They used multiple spectral inputs, included methanol, considered the lack of a strong normal water line, and built a physically consistent picture of what the coma could and could not be doing. Could later work refine the picture? Absolutely. It should. That is normal science. But for the whole result to vanish, you would need a major hidden effect large enough to fake an enormous deuterium enrichment. That is a much taller order. Again, that is why people are taking this seriously. Let's also think about what the result means for theories of disk mixing. One major idea in planetary science is that young disks are messy. Material moves around, pebbles drift, gas circulates, turbulence redistributes things, snow lines move. Heating events reset chemistry. If that is always very effective, then many systems should partly homogenize their water chemistry. 3i Atlas suggests that some systems may not homogenize nearly as much as ours did. That is not a small point. It means we may need a broader menu of disk evolution pathways. Some systems may be highly mixed kitchens. Others may keep their ingredients in separate bowls, and that difference can shape the chemistry of everything formed there: planets, moons, comets, atmospheres, ocean inventories, all of it. Now, could 3i Atlas come from a system with no planets at all, just a disk, and later ejection by a passing star? In principle, maybe. But giant planet ejection is a very efficient way to produce interstellar objects. So many researchers suspect such systems often had major planets involved. Still, even that uncertainty is informative. It reminds us that small body ejection is tied to system architecture, and every interstellar object is partly a fossil of that architecture. There is also the question of whether 3i Atlas formed in a binary star system. Binary systems are common in the galaxy, and their dynamics can be excellent at ejecting small bodies. A binary environment could also affect disk temperatures and evolution in complicated ways. That is speculative for now, but it is one more reminder that there are many ways to build a system very unlike ours. And if the galaxy is full of such systems, then our local standards may be very local indeed. Now let's return to habitability one more time, but carefully. When people hear different water chemistry, they instinctively ask whether planets in such systems can still have oceans and life. The answer depends on scale. The DH ratio measured in a comet does not automatically become the exact DH ratio of an entire planet's oceans. Planets receive water from many sources. They process it geologically and atmospherically. Hydrogen can be lost to space. Oceans and mantles exchange volatiles. So there are many steps between a comet's isotope ratio and a planet's final water inventory. That means we should not jump from word comet to all planets there are biologically doomed. That would be silly. What we can say is that the raw materials available to young planets may vary more than we assumed. And that means pathways to habitable conditions may also vary more. This is actually a more interesting result than a simple yes or no. It says the universe may build potentially habitable worlds through a wider set of chemical routes than our own history alone would suggest. That could be good news for life. Or it could mean some routes are less friendly. We simply don't know yet. But it definitely means habitability is not one size fits all. Now, I want to touch on the emotional side of this discovery, because space news is not just information. It changes how we imagine our place. There is something deeply moving about the fact that a small frozen body from another star system can teach us this much. It is not a giant planet, not a nearby habitable world, not a flashy black hole image. It is a dirty snowball, a chunk of ice and dust thrown out of its home long ago, wandering alone through the dark. And yet inside that little object is a chemical record of a lost birthplace, a clue about another sun, another disk, another set of planets, maybe another history. We cannot see that system directly. We may never know its name. But through this comet we get a glimpse. That is one of the things astronomy does best. It makes the universe feel enormous and intimate at the same time. Now let's be practical again. What should scientists do next? First, get more observations while 3i Atlas is still bright enough. That means more ALMA time if possible, more infrared observations, more optical monitoring, and any chance to detect additional molecules. Second, refine the models. Better coma models, better line transfer calculations, better temperature constraints. If the exact DH value can be pinned down more tightly, that will help a lot. Third, compare 3i Atlas with disk chemistry models in a systematic way. What combinations of cloud temperature, disk evolution, star type and mixing can reproduce such a high DH ratio in cometary water? That will narrow the plausible birth environments. Fourth, prepare for the next interstellar object, improve discovery pipelines, coordinate rapid response observations, build mission plans that can react quickly. The best way to understand whether 3i Atlas is rare is to be ready when number 4 shows up. And fifth, resist the temptation to over-explain too early. One object is powerful, but a field grows by staying humble in front of the data. That humility is especially important because interstellar object science is still basically in its childhood. We are building the language as we go. Now let me say something about why Nature Astronomy publishing this matters. Peer review is not magical. It does not guarantee truth forever. But it does mean the result passed expert scrutiny before being presented to the community as a serious claim. Other scientists looked at the method, the data, the interpretation, and judged it strong enough to publish in a major journal. That matters especially for a result this surprising. Astronomy has no shortage of dramatic claims that fade. This one has enough backbone that the field is treating it as a real shift, not just clickbait with equations. And yes, it will still be tested further. Good science always is. Now, I want to bring back an earlier theme. Serendipity by 3I/Atlas was not discovered because humanity built a special interstellar comet hunter with this exact goal in mind. It was found by a sky survey doing broad monitoring work. That is a big reminder of how discovery often happens. You build general purpose tools, look carefully, and stay open to the unexpected. A lot of major discoveries work that way. The universe rarely gives you the exact thing you predicted on the exact day you scheduled. It throws curveballs. Good science is having enough tools and enough curiosity to notice when one passes by point 3I Atlas was a curveball, and because people were ready, it turned into a scientific event. Now let's imagine the future for a second. Suppose in the next 10 years we find 15 more interstellar objects. Some are inert rocks, some are active comets, one has familiar water. One has almost no volatiles. A few have isotope ratios between Borisov and 3I Atlas. One is even more extreme. Suddenly we could start building a true map of extrasolar small body chemistry. That would be incredible. We could compare objects statistically, link compositions to likely birth environments, and maybe even identify major classes of planetary systems based on the debris they throw into space. Not from planets themselves, but from the leftovers they eject. That would be a brand new branch of galactic archaeology. And 3I Atlas would be remembered as one of the first objects that proved the field mattered. Let's also not miss the fun irony here. For years, humans tried to answer big questions about alien worlds by staring at distant stars and planets directly. And yes, that is still essential. But at the same time, some of the best clues may come from scraps. From the trash, basically. From the stuff systems throw away. That feels very on brand for science. Sometimes the best way to understand a house is not by looking at the roof, but by checking what is in the bins. Interstellar comets are the bins, and 3I Atlas had something weird in it. Now let's tighten the chain of logic one more time, because this is the core of the whole story. A comet from another star system entered our solar system. It showed cometary activity, which meant scientists could study the gases coming off it. Early chemistry already looked unusual. Then ALMA detected HDO, a form of water containing deuterium. Regular water was not confidently detected at the expected level, which let scientists place a strong upper limit on how much ordinary water could be there under the observed conditions. Combining the HDO detection and the upper limit on regular water gave a very high lower limit for the DH ratio. That lower limit is at least 30 to 40 times Earth's ocean value and far above solar system comet values. Such a high DH ratio points to water formed or preserved in much colder and less processed conditions than the water in our own solar system's comets. That means the parent system of 3I/Atlas likely formed in a colder, quieter, or less mixed environment than ours, or at least preserved those early chemical signatures much more effectively. That single result challenges the idea that water chemistry in planetary systems is broadly universal. And because water is central to planet formation and habitability, the result has implications far beyond one comet. That is the chain, no fluff needed. The story is strong enough on its own. Now let's go a bit more poetic without getting weird, because I think this discovery deserves it. For billions of years, chemistry has been writing little notes inside ice. Stars form, disks spin, planets grow, comets freeze. Systems collide and throw things out. Most of those notes remain locked away, too far for us to read. But once in a while, one of those notes drifts close enough that we can finally open it. 3i Atlas is one of those notes, and the message inside is simple but enormous. Your solar system is not the only way to build water. That is the kind of line that changes how you see the sky, because it means every star system may carry its own chemical accent, its own way of assembling the ingredients of planets, its own version of familiar things. We are only just beginning to hear those accents. Now, since the hook at the start was meant to be more grounded, let's end grounded too. What is the safest big takeaway from all of this? Here it is. 3i Atlas is the third confirmed interstellar object and only the second interstellar comet whose chemistry we can really study. Its gas already looked unusual. Now its water appears to be extraordinarily rich in deuterium. That makes it unlike anything we know from the solar system. The simplest interpretation is that this comet formed in a colder, less processed environment than the one that shaped our own comet population. That means planetary systems across the galaxy may preserve water chemistry in much more diverse ways than we assumed. And if that is true, then the possible starting conditions for planets, and maybe for life, are probably wider than the solar system alone, led us to believe. That is why astronomers are so excited. Not because a comet showed up, because a comet showed up carrying evidence that the universe is even less standard than we thought. And honestly, that is one of the best kinds of news science can give you. A frozen visitor from another star system passed by the sun, started boiling into space, and told us our local recipe for water might be just one recipe among many. That is not a small update. That is a change in perspective. It reminds us that every time we think we have a decent grip on what normal looks like out there, the universe laughs a little and sends something like 3i Atlas through the neighborhood. And this is probably just the beginning. The next interstellar object could be quieter, stranger, simpler, or even more extreme. It may confirm what 3i Atlas is hinting at, or it may open another door entirely. Either way, the era of interstellar object science is no longer hypothetical. It is here. We are not just looking at distant systems anymore. Pieces of them are coming to us. And now we know those pieces can carry chemistry wild enough to rewrite some of our assumptions. That is a wonderful place to be in science. Early enough that almost every new object can surprise you. Advanced enough that you can actually measure the surprise. So, yes, 3i Atlas is just a comet. The same way a fossil is just a rock. The same way a page from a lost book is just paper. The value is in what it preserves. And this comet preserved a story of cold birth, chemical memory, and planetary diversity that we badly needed to hear. If you want the next strange clue the universe just dropped in our path, watch the video on your screen.